I'm trying to keep up with my uploads, and when I say so, I mean I update this section of the algebra component on Moodle, the one which I call the in-class lectures. This morning, I uploaded a full recording of the lecture before on YouTube, and I made a link available here. I know you have Eco360, and I'm fine if you use Eco360 if you like it. If you don't like it, you can use it here on YouTube. Plus, on the top of the video on the YouTube of the last lecture, I also, here, if you go here, I also put the short notes, the PDF files with the short notes, the screenshots of the slides you saw 2 days ago. So it's your choice whether you go Eco360, you go here. I'm totally, I don't care, but I keep it especially because for the next year, for instance, Eco360 is no longer available, but for my own records, I'd like to keep every recording handy. Okay, and that I'll try to keep up. Like I said, for the second lecture, I'll make another upload, for the third, for the fourth, and so on. So, now I think we're ready to discuss what the complex numbers are. So when you introduce the complex numbers, you do it in easy way. You introduce the complex numbers through what is called Cartesian, or sometimes I call it algebraic form. It's basically what you do, you just take real numbers and you just add to the set of real numbers one extra element, which you call I. And that's the number which is with a specific property that if you square it, it returns -1. And when I say you combine R with this element, it means you combine it in all possible algebraic ways. So eventually you will end up with the structure like so. So you will have every complex number, basically, it will have a form. And that's the form which I'm going to call algebraic form or Cartesian form of a complex number. So it's a combination of two real numbers when one of these real numbers is scaled by this imaginary number, imaginary unit I, newly introduced, newly crafted number I. Like I said, if you remember our discussion from 2 days ago, I said that by just introducing one extra number like this, by introducing this I number into the set of reals and making these combinations A plus BI, it's a simple thing if you think about that. It's very simple that we just throw in an extra number, but by just doing this little simple thing, we achieve a tremendous result. Remember from 2 days ago, I told you that any equation in complex numbers will be solvable within complex numbers. It's a miracle if you think about that. By doing this little thing, you end up with, you achieve so much. It is a miracle. It's a miracle around the complex numbers, which we now enjoy. So if you comments about the terminology, this thing which we call algebraic or Cartesian form of complex numbers. What else there? The components which appear in Cartesian form of a complex number, they bear their own name. We call this a real part of a complex number. We call this the imaginary part of a complex number. I think we have a special notations for that. Z or im z. It's a minor thing, but my experience tells me that many people trip on this. Imaginary part of a complex number, this symbol, it doesn't include the I with it. Don't make this silly mistake. It's not a big mistake. If you make such a mistake in your test, probably if I will be marking your test, which is not a certain thing, I will overlook this, but some tutors may penalize you for that. Just keep in mind, the imaginary part of a complex number never comes with the I. Imaginary part of a complex number by itself, it's a real number. Right. I don't know if you're familiar with this. I expect you're familiar with this notation, but this symbol, we normally read this symbol belongs to. So when you say something like this, it means Z comes from the set of complex numbers or belongs to the set of complex numbers. So the main thing we should know about the Cartesian form is the way we do arithmetic with complex numbers when they are given in Cartesian form. This is the simplest way to do the arithmetic with the complex numbers, the simplest to remember. to some extent the simplest to perform. There are some other ways, trigonometric form, for instance, we discussed it today. In Cartesian form, if you have two complex numbers, both given in their Cartesian form, so you see I use four letters A, B, and C, G to denote the real and imaginary parts of these two complex numbers. Four operations as we know them, the operations we discussed with you 2 days ago: addition, multiplication, and this time I will replace the negative with the subtraction operation, which is equal to that, and the inverse with the division operation. In complex numbers, you can perform them by just doing some special tricks on the imaginary and the real part. That's all there is to it. So, for instance, if you plus or minus two complex numbers, this is as good as if you plus and minus the corresponding imaginary and real parts. When you multiply, the trick is a little bit. The rule is a little bit longer. You have to do basically the regular expansion as if the real numbers. So when you multiply two complex numbers in the Cartesian form, all you do like a regular expansion. You just multiply each by each effectively, A by C, A by D, B by C, B by D, and you keep in mind that when you multiply I by itself, when you come up with the I square, it's just -1. That's all you have to do. If you do this expansion, you will end up with the formula for Cartesian form of the product. There will be a formula for the real part, new real part. There will be a formula for the imaginary part. That's all there is to it. To some extent, the hardest operation is the division. Probably the hardest is not a good word here, just it's the longest to perform, or the longest to write up. In principle, if you remember the main driving idea of the division, it's not really that hard. And the main driving idea of the division is this. If you have two real numbers, and this time I call them x and y, if you have two real numbers, which I call x and y, and if you build the product of this type, so you see I took two complex numbers, x plus iy, and x take iy, we know how to multiply them. It's just a line above it. That's the line how to multiply them. If you multiply them, and I will skip some details, you see I use the dots to hide some details. If you do this expansion in full, and if you do simplifications, you will realize that all what will be left is this number, which is a real number, by the way. Surprise, surprise. You multiply two complex numbers, but you ended up with a real number. This is a trick which drives the whole idea behind division of complex numbers. And this is a trick, actually, which is worth remembering on its own. If you remember this trick, you can do a few shortcuts in many computations in complex numbers. So not only this is a trick which helps a lot when you divide complex numbers, this is a trick, like I said, it's worth remembering on its own because it will help you. So let's just see how we use the trick when we divide two complex numbers. Again, if I use these two complex numbers, z and w, and if I intend to find the quotient, z on w, if I intend to find such a quotient, look what I do. Here's my quotient of two complex numbers. This is just a formal writing of this quotient. I replace z and w with the Cartesian forms. The trick comes here. You just introduce an extra factor, which effectively is a unital factor, right? I just introduce the factor like this. That's the 1, right? If you just cancel it out, it will be 1. But you don't cancel it out. In fact, you combine it differently. You combine things in the denominator together. You combine things in the numerator together. In the numerator, when you combine them, you just do regular product algorithm, this algorithm. But in the denominator, that's a trick. That's where you're going to use this trick. And in fact, in practice, when you do this, when you do quotients of complex numbers, you hardly will be expanding the bottom. You will be just jumping straight away here, if you remember this trick. You hardly be doing these computations which are hid behind these dots. So here's my expansion. Here's the expansion of the numerator according to this algorithm, and that's the trick which I applied here. And the good thing is, because this is a real number, or because this is a real number, you end up with something. You end up with a complex number in the Cartesian form. So you end up with something which again have this structure: real part, imaginary part times r, and that's all there is to it, isn't it? Well, you can of course do like you can do the expansion. You can write separately the real and imaginary part if you wish, but that's just a cosmetic change. This is just a cosmetic change. Any questions? I'll show you a few examples. I'll show you one simple example, and then I'll show you one more involved example. Yeah, it's here on this side of it, on this side of the slide. So it's a simple example. So I chose randomly two numbers, say these two, which are now, we have full endorsement to call these complex numbers, two real numbers combined with I next to it. You can compute, the example says find the sum, find the difference, product, and quotient. I'm not going to go for the product, for the sum and difference. Nothing can be easier than this. Or maybe I can. What's that? No. I'll just make a demonstration for the quotient. Look at this. If I go after the quotient of these two complex numbers, one and the other, I do my trick. I introduce this extra factor, unit of factor, so I use the denominator number, but I build a new complex number with a negative rather than positive. And then I can do the expansion. When I expand the enumerator, it will be 2 times 3, which is 6, and then it will be negative 4 times negative 1, and another negative, so it's a, once again, 2 times 3 is 6, and negative 4 times negative 1, it's plus 4, with another negative, it's negative 1, and negative 4, so that's why it's 2. 6 take 4, it's 2. The imaginary part comes up when you multiply 2 by I, negative 2, and negative 4 by 3, which is negative 12. That's why it's negative 14. At the bottom, you do the trick, 3 squared plus 1 squared, which is 10, and that's the result. You can split them if you wish into real and imaginary part, and that will be the quotient in the real and imaginary part. Any questions? I will do one more advanced example with the computations. It's a tutorial question from Yellow Book. It's a tutorial question 9. The question says, question 9 from the tutorial book, it says compute the expression of this type. So this time when I do this example, I will use only the Cartesian operations, even though the number looks the number itself is rather complex. I will show you that you can compute this number and the result relatively easy, relying only on the Cartesian operations. So look at this. Let me ask you this. If you look at the question like so, and you have to compute this only with the Cartesian operations, the ones we just discussed, what would you do? Any suggestions? Binomial, do you think? Well, the first thing which comes to you, you may try binomial expansion, right? You can use binomial expansion, which says this. This is a binomial expansion for the cube. You can use that. The thing is, if you try to use that, you will end up with a, look at this, what's going to happen. You're going to take this as A, you're going to take this as B, and you can do this expansion. I even started this expansion here, so you can do binomial. I even started this expansion here. You see it's A cubed, because this comes for A. This is the second term in the binomial expansion, square of A and B, and many others. But then if you do binomial directly, like suggested, then you have to do binomial here, here, and in the other terms as well. In fact, in principle, you can finish this, of course. In principle, you can use multiple binomials. I mean one after the other, and end up with the answer. But there's a better way. Do you see a better way? Again, a better way to compute this relying solely on the Cartesian operations. Any suggestions? What if I do a slight rearrangement under the cube expression? So this expression which sits in brackets, I mean in square brackets. If I do a slight rearrangement, if I do this rearrangement like this, maybe this helps. Maybe this will help you to see a better way to compute this. Again, relying solely on Cartesian operations. Any suggestions? Oh, no suggestions? Something beautiful, something tricky, or something smart. Imagine you're on a test and you need to compute this with the extra condition. You need to use only the Cartesian operations. What are you going to do? If you go down the binomial way, you will stuck somewhere in 15 minutes, and all your time will be up before you finish. Well, the trick here, and later on maybe I'll show you why this trick actually. It's relatively obvious why you need to do this trick. The trick is this: you can factor one of these numbers out of this bracket. At first, when you think about that, I mean these brackets, one of these brackets as a whole, you can factor them out of the cubic expression. I'm not sure which one I'm taking here. I'm taking the first one. So look at this. I can take the first expression and take it out as a factor. And then I will end up with something like this, right? If I factor this bracket, you will end up with the unity in the first place, and in the second place, it will be a fraction like this. At this stage, you may wonder whether this is getting any simpler than the original one, but in fact, as soon as you finish this quotient, as soon as you finish the computation of this quotient, the way we need to compute the quotients relying solely on the Cartesian operations, you will see that it does become simple. Look at this. Here's my quotient. If I compute this quotient, I use the algorithm we just discussed with you. I just introduced this extra factor, unity factor. So I took the number in the denominator. I introduced the unity factor with the plus and plus. At the denominator, I will use my trick, which is the sum of the 3 and 1, 10. In the numerator, if you do the expansion, that's a complete expansion in the numerator. This root 3 by I, it's this negative root 3. This one by this root 3 is this root 3. And the imaginary part comes up if you take this I root 3 with this root 3, it's 3I. And this one and this I, that's I. That's the expansion for the numerator. Denominator, it's just a trick. 3 plus 1, it's 4. And it looks like lots of things cancel out. Root 3 cancels root 3. And you got I as a result. So you need some insight, of course, to predict this to happen, because when you just decide to factor this out, it's not yet clear whether the result will be simpler, but with some insight, and I'll discuss how to gain such an insight a little bit later, you can expect that when you do that, this second term here, even though originally it looks not so simple, if you perform the Cartesian operations, the term in fact will be simple one, just I. So basically we're almost there. The whole thing now, the whole expression we need to compute becomes the expression of this type. First factor, and 1 plus I. This is I for this quotient. And now we can use the binomial twice. So you cannot avoid binomials in this example. I mean, this binomial expansion. You cannot avoid this. You need to use it. But if you compare this with the direct computation, when you first do binomial on the whole expression and then you do binomials on individual terms. This way it's a lot shorter because you only need to do binomials twice. One for this factor and one for this factor. So here's my binomials. That's the binomial for first factor. I'm hiding some computations with the dots. Actually, I'm not hiding much. The cube of root 3 is in here. 3a squared b is in here. That's right. B is negative 1i. 3ab squared is in here, and the b cube is I right here. All in all, after all simplifications, it will be negative 8i. Similar binomial for the second factor, 1 plus I cube. Similar binomial expansion. This is the expansion, and that's the result. You're subbing in the computations in here and in here. And that's the 16 plus 16i. Yeah. Any questions? Can I ask you this? This solution we just discussed, it's a good solution, very effective solution. I don't think you can come up with the easiest solution even if I remove this extra requirement that you have to rely solely on Cartesian operations. Even if I lift this requirement, computing this example with any other ways which exist in complex numbers, it's not going to be shorter or much shorter than this. Do you see the reason, or do you see this idea which suggested such an approach? Okay, if you don't, then I'll show you this to you in 15 minutes, hopefully. All right, so basically, if we manipulate with complex numbers only with a Cartesian way, it would be quite boring. And to see some exciting examples and to be able to do harder examples, we need to discuss with you other ways to manipulate with the complex numbers. These other ways involve geometric interpretation of complex numbers, something which we call trigonometric or exponential form. Let's just look into that quickly. Right, so again, a few new terminology elements. Modulus, argument, conjugate, that's three things which are, the hardest probably will be the argument, the hardest to get the grip of. Right, so for a complex number given in Cartesian form, you can introduce a few extra concepts attached to it. Some of them, these are real numbers. So these are the conjugate complex number, something we used a few times already when we did division. Now we just give the official name to this combination. When you take a complex number, when you revert the sign next to the imaginary part, when you do that, that will be a conjugate complex number. The trick which helped us to do division so well, in these new notations it will look like this. If you multiply a complex number by its complex conjugate, it just spits out sum of the squares of the real and imaginary part. Another thing which is attached to a complex number, which is called the modulus of a complex number, or an absolute value of a complex number. That's something which we compute like so. And if you combine this with this, you'll have another formula for the absolute value of a complex number. It's a root of the product of the complex number with its complex conjugate. I think when you introduce the modulus, you can immediately see some geometrical interpretation for the modulus, because that resembles a lot the Pythagoras, and that's what inspires the geometrical interpretation of a complex number. what you do, you just build a vector which originates from the origin and which stretches all the way to the point with the coordinates given by A and B, like this. So if this is a point A, and this is a point B, then this blue vector will be the vector which represents my complex number Z. The absolute value of your complex number, in this case, in this geometrical picture, it will represent the length of the blue vector through Pythagoras. And if you continue on this geometrical interpretation, you can introduce a name for the angle. That's something which we're going to call the argument. So if this is the angle, alpha, the other name for this alpha will be, or the other notation for this alpha will be argz. And like I said, the argument is the hardest of all because the direct formula for the argument is not so simple to remember, let alone to prove or come up with. Well, direct formula for the argument looks like this. It is the arc cos of the two different arc coses depending on your imaginary part of your complex number, but that's the formula for the arc. On the bright side, even though the formula looks quite complex, on the bright side, there will be quite few, or just a few occasions where you will need this formula directly. On many occasions, you will be able to guess the argument from your knowledge of standard sine and cos values. But like I said, there are a few occasions in the yellow book where you need to know the direct formula, full, complete direct formula for the argument, and here it is. It's not an easy formula, it depends on the sign of the b, but still it's a complete and correct formula. Having these angles and having the length of a complex number, you can give trigonometric expressions to a and b. If you do that, your complex number will take the form of this type. And this is something which we call trigonometric form of a complex number. Trigonometric form of Z. Yeah, right. Trigonometric form of Z. Another comment which is in order here probably is this. When you manipulate or when you deal with the trigonometric form of a complex number, this alpha angle, which appears here, you have some flexibility with this angle. I mean, one way to determine this alpha, of course, is through the formula for this formula. But there is some flexibility which is coming from the fact that the sine and cos functions, they are periodic functions with the period 2 pi. And that means that if you replace this alpha angle here, with another angle, which is larger than alpha by 2 pi, the formula will stay the same. That's the periodicity of sine and cosine. In fact, you can add any multiple. You can add any multiple of 2 pi, and that will not change the trigonometric form. So this is on the one hand, it's a great flexibility. With the right skills, you can employ that flexibility to your advantage quite effectively. On the other hand, it may cause some confusion. So argument of a complex number, it's not a unique thing. It's defined up to the multiple of 2 pi. Any multiple of 2 pi. This specific argument, which is given by this specific formula, it possesses an extra property that it sits within these two bounds. Not every argument sits within these two bounds, but the one which is given by this particular formula, it does. And that's why this specific argument, which is denoted with the capital A, it bears a special name. We call it the principal argument of a complex number. Any other is just an argument, but this particular one is the principal one. Any other one is the principal one plus a multiple of 2 pi. Okay. So that's what we mean when we say trigonometric form of a complex number. The main advantage of having trigonometric form is the way we can do multiplications and divisions of complex numbers. and by implication powers, and that's something I'm going to discuss next. Let me open that. That's a special slide which I call trigonometric and exponential forms. So now I can start off. I can start off with two complex numbers, but now I will start off with two complex numbers in trigonometric form. So the complex numbers with the moduli r and q, and with the arguments alpha and beta, not specifically principal argument, in fact any argument will do. The beauty or the great discovery which came right after the people discovered the trigonometric form was this. If you attempt to multiply these two complex numbers in this generality, if you attempt to do that, and if you do it the way we do it with the way we do Cartesian multiplication, the one we discussed 2 slides ago, that's a nice challenge actually, and I don't do it in class, but you can try to attempt this. If you do the expansion, if you identify the resulting real and imaginary part, and if you employ some formulae from the elementary trigonometry from the high school, you will realize that the product will take this form. Once again, if you multiply these two complex numbers the way we multiply complex numbers in Cartesian form, it will be some combination of the real and imaginary parts of the original factors. Through some formulae from trigonometry, you will realize that the real part of the resulting product will take this form, and the imaginary part will take this form. When people first discovered this, it was a surprise, because you see, in trigonometric form, multiplying complex numbers takes quite easy algorithm. All you need to do, you need to multiply moduli, you need to add the arguments. When they discovered that, they just jumped straight away to division and said, maybe division also so simple, and in fact it is. If you do a division, Cartesian division of these two numbers, if you do a Cartesian division of these two numbers, and if you employ some formulae from trigonometry, you will see that the result will take this form. When mathematicians realize this, they realize that multiplication and division of complex numbers in trigonometric form takes such an easy structure. They saw the analogy straight away. They saw the analogy with the way exponentials behave. They saw the analogy with it because when you multiply two exponentials, basically you add the exponents, isn't it? Something which you observe quite often with exponentials of real numbers. So they said this bracket, forget about the other factor r, which is a real number, by the way, just something we know very well. This bracket, which carries the genuine, the true complexness of the number, right? Because the I number sits in here, it behaves as exponential. That was a great discovery and a great suggestion. They said, why don't we just take this bracket and call it the exponential? It was a great discovery by Euler. And that's something which now we call the Euler formula. We just define a complex exponential, or we just define this expression to be the exponent or exponential of the same type. You cannot prove this formula. It just was a convention originally, and this convention proved to be very beneficial, very good, and that's why we keep this convention since the time it first was made. And this convention solely relies on the fact that this bracket behaves like exponential. Right in here, when you multiply two brackets like so, you just add the argument. When you divide two brackets like so, you just subtract the argument. In fact, you can take this. In fact, if you use principle of mathematical induction, you can take it even further. You can say if you compute powers, that will be as good as multiplying the argument by n, and it's another evidence which supports the idea of the Euler formula. That's another point which supports that idea. So if you use this idea, of the Euler formula, you can basically, in fact, you can think of this symbol as a simple abbreviation to this longer one. In fact, I think it's the best way to think about this the whole thing. Complex exponential, yes.
Why do you put a colon in front of the equal sign?
Why do I put a column in front of the equal sign? It's a good question. Normally when people write something like this, they mean equal by definition. When someone puts a column in front of an equal sign, you just read this, not just equal, not just an equation, not just something you proved, but something you make a convention about. So here we're making a convention that this symbol, it's the first time this symbol appears in our joint study of complex numbers. This symbol will simply represent this longer line. And the justification for such a choice of notation is here again, because this longer line, which has quite a concrete meaning, it behaves like complex exponential. With this abbreviation, I use the term abbreviation not accidentally, because this is just an abbreviation, nothing else. We just convene together or agree together that this will be called EI alpha. With this new convention, new abbreviation, or new notation, my writing takes a lot shorter space, isn't it? Because the whole thing now of this long, which is this long, can be written as short as this. And the W thing can be written as short as this. The multiplication rule can be written as short as this. The only advantage of this is just making things shorter. Nothing else, yes?
But if you use some other standard definition of E, is that not true?
Which other definition of E? There's no any other. I'll surprise you here. Do you know any other definition of E of a complex number? So you said if you use any other, which other do you know?
For instance, the limit of n goes to infinity of 1 plus 1 n.
You mean the one which is defined through the series?
Yeah.
Well, it's a good definition. If you use that as a definition of E, I don't say this is bad, but you will face significant difficulties, because then you will need to prove this. Then you like the question which came from back there. Then you have to kill this colon here. You no longer will be able to say that, because this symbol now will have different meaning, the one we just suggested, is serious meaning, and then you have to put some argument behind this equal sign.
Is there such an argument?
Yeah, of course, with some effort you can come up with such an argument.
So there is proof.
The proof may be found, that's right. The proof may be found, that's right. But from if you do it this way, you can do it this way, but I don't consider this the best way to introduce the complex exponentials. But it's a good comment. You can, in fact, introduce exponentials through infinite series. You can introduce it like this. You can do through infinite series. I'm not going to lie to you. There are some other ways to introduce exponentials, but they are they don't represent much of the practical interest, actually. Where were we? Oh, okay, so I was talking about how short this writing become if you use complex exponentials. That's the shortening of the quotient rule. This is a shortening of the taking power rule. Yeah, that's a shortening of taking power rule. That's right. Any questions? Any further questions? Right. Sometimes you will see the term converse Euler formulae. So this is a line which bears the title Euler formula. Someone says Euler formula, it's the thing which you have to come up in your head straight away. If somebody says converse Euler formula, it's just a derivative of this formula, where you just express cos and sine in terms of the exponentials. That's the way to do it. You can express cos through exponential like this. You can express sine through the exponential like this. The other term which is attached to this slide is the de Moivre theorem. It's a theorem which actually, I have said it already, I said it here. The de Moivre theorem, we keep the name for historic purposes mostly, and for the reference purposes also. De Moivre theorem is this identity, which is written right here, where you just replace R with unity, and that's the way that's the form it takes if you replace R with unity. The left-hand side here comes from here. The right-hand side here is right in front of you. If you wonder what the proof is, it's just basically I already guided you through the proof, because all you need to do first, you need to establish this identity. You have to recover the argument which is hid by these dots, and then you have to use the mathematical induction to bring it to the power n, and that will be the proof of the de Moivre theorem. In fact, that will be the proof of the stronger result of this identity. Another thing which normally probably I should mention on this slide, it's the thing which I mentioned already about the argument being not a unique thing. It's a thing which is used often when you solve equations involving complex exponentials. And it is this: if you look at the identity between two exponentials, ei alpha and ei beta, and again you interpret these exponentials just as abbreviations for this longer writing, cos and sine writing. You can, if you attempt to solve for the exponents in this exponential equation, you can do it, but you have to keep in mind that the argument is not unique. It is always by modulo 2 pi. So 1 alpha equal beta plus some factor of 2 pi. Okay. Any questions? Well, the last example I'd like to discuss, but we have 5 minutes left. It's the same example we just did, the question 9 from tutorial book. But this time you will see why I chose this factoring method, because the question 9, you can do this question with exponential forms. And when you do that question with the exponential forms, this trick, which appeared quite coming out of the blue when we try to do it in pure Cartesian terms, this trick comes out like as a natural suggestion there. Look at this. Yeah. I have quite a lot of material actually already collected. So it's a question 9. The same question, we compute this expression as before, but this time we will try to use exponentials. Like I said before, the solution will not be shorter by any way, but the trick, which was no one actually suggested that trick when I asked you. This time the trick will be just very clearly seen from the expression itself. Look at this. So what I will do first, I'll do the same rearrangement as before. The same rearrangement I did before, but this time I do it, the same rearrangement. And now I try to convert my numbers in these smaller brackets to exponential forms. Look at this. When I look at this number, first I ask myself, what's the modulus of this number? The modulus of this number is sum of the squares, so it's 2. I factor the modulus out. That's what is left. And then by looking at these numbers, I try to guess the angle for which the cos will be √3/2, for which the sine will be -1/2. This is a point which explains to you that this formula for the argument I showed you a few slides ago, it's not often needed. Most of the time you can guess the argument basing on your knowledge of the standard values for the cos and sine. So if you're struggling to guess the argument where I guess it quickly, it means that you have to refresh your memories on the standard values of sine and cos. In this case, the choice for the argument is negative 0.6. Good choice for an argument, I mean. You can, of course, add 2 pi or subtract 2 pi depending on your preferences, but like I said, the main idea here, when you convert a number to complex number to trigonometric form, most of the time you can rely on your guessing machine. If your guessing machine doesn't work as good as mine, you have to work on your guessing machine. So for this number, here's my exponential form. For the other one, for the second number here, what just happened? Something just happened, my apologies. It always happens in the least expected moment. For the other number, for this number, again, I identify first the modulus of this number, which is 1, it's 2 again. And then I guess, and then I use my guessing machine to identify the argument. For these two numbers, 1/2 and √3 on 2, the angle which supplies these two numbers as cos and sine is the 0.3. So here we go. I convert both of these numbers to exponential forms. Now I will do the replacement. Look at this. If I replace them, well, both of these numbers have the same modulus, 2, so I can factor it out. That's why it's 2 to the power of 3. It's this cube. Inside the brackets, I have two exponentials. Here they are. And now when you look at this, you can see why in my first computation I suggested to factor one of the terms out. Because if you do factoring out here, the way we do manipulations, the way we do divisions with exponentials will suggest that this 0.3 plus this 0.6 will deliver pi on 2, the angle for which the complex number takes very simple form. This is the idea which suggested that I need to factor there. So knowing complex exponentials, knowing these computations for the complex exponentials suggested how to do the computation without any reference to complex exponential, but yet in effective form. This is very typical in mathematics. You knowing more, even though I didn't show this knowledge to you in my first computation, right? I didn't say a single word about cosines or sines or exponentials or trigonometric forms. I didn't do it, and yet I made very effective computations. It's very typical actually in many sciences. The knowledge you have, even though you're not exposing that knowledge, makes you more advanced in comparison to the others. The knowledge of the trigonometric forms, even though I didn't expose it there in my first computations, made me compute it a lot quicker in comparison to the direct computation for the binomials. So if you factor this out, we don't have time for this to finish. I will upload this complete slide with the rest of the computations. In fact, I encourage you to finish this on your own with exponentials, but I will upload the complete computations with the video, complete video. If you struggle to do it on your own, to finish it on your own. Excuse me. Sit down, everyone, please. I know you're tired. 2 hours of mathematics, for some of you apparently not something you can sustain easily, but it's your choice. You came here. It's your choice. It was your choice to sacrifice 1 hour of your life to discuss things with me, right? So your 1 hour of your life is still going, so I'm taking my sacrifice yet. But actually I'm done already. Thank you very much. You're free to go.